To safely power everyday appliances, like an electric space heater, the high-voltage electricity traveling across the power grid must be stepped down to a usable level. That conversion happens inside a transformer. If you look closely, you'll find layers of wrapped copper wire tightly coiled around a core. The exact number of these wire wraps is a calculated design requirement defined by the transformer EMF equation. Voltage equals 4.44 times frequency times the number of turns times the maximum magnetic flux. To find the required turn count, we isolate N by dividing the target voltage by the rest of the variables. Calculating this specific turn count allows an engineer to match a physical spool of wire to the invisible magnetic forces generated by the power grid. Let's look closely at the denominator, starting with that specific number, 4.44. That value is a mathematical constant derived directly from the geometric shape of a standard alternating current sine wave. Next is the maximum magnetic flux, represented by psi m. Specification sheets often measure this in milliwebers, but the formula requires you to convert that value into base webers before you begin the calculation. Notice the mathematical relationship. Because frequency and flux are in the denominator, they are inversely proportional to the number of turns. As either value increases, the required amount of wire decreases. Precision is critical here, because an underestimated flux value can drive the core into magnetic saturation. When the core saturates, the winding loses its inductive resistance and draws excessive current, which can melt the insulation and destroy the transformer. This inverse relationship is why a system operating at lower frequencies requires a massive spool of copper wire, while high-frequency designs use far smaller, lighter coils. Let's try a design problem. Calculate the turns for a coil that outputs 240 volts at 50 Hz, using a core with a maximum flux of 0.012 webers. Pause the video now. Plug these three values into the rearranged equation and solve for N. Place 240 in the numerator for voltage. In the denominator, multiply our 4.44 constant by the 50 Hz frequency and our flux of 0.012 webers. The result is 90.09. Since you cannot wind a fraction of a wire loop in a standard design, you round to the nearest whole number, 90 turns. The math in the denominator defines the physical limits, the weight and the material cost of the copper winding. This calculation is the technical blueprint used during industrial assembly to ensure each winding meets its exact power requirements. Let's review the core rules for your cheat sheet, starting with the target equation isolated for the turn count, N. Rule 1. Always verify your units. Magnetic flux must be entered in webers to avoid saturation errors. Rule 2. Higher operating frequencies require fewer turns of wire due to their inverse relationship in the denominator. Mastering this equation provides the mathematical link between magnetic theory and practical manufacturing, ensuring that power remains stable and predictable across the grid.